Okay, let's check out logarithmic equations now. There are two types of logarithmic equations we're going to be looking at. In type 1, our logarithmic equation can be written as log base b of f of x equals c. So essentially we have a logarithm on one side of our equation and it equals a constant. When this is the case, we're actually going to be able to play the circle game or do the log roll, and we are going to rewrite it as an exponential equation and solve. Okay. Now, our second scenario is when it can be written as log base b of f of x equals log base b of g of x. Now, in this case, notice that I have logarithms of the same base on each side of the equation. In this case, then we can rewrite as f of x equals g of x. So if the logarithms have the same base, then we can set their arguments equal to each other. Okay. Now, super duper important when we are talking about logarithmic equations, you have to check your answers. Okay. Think about the domain of a logarithm. Okay. My domain of a logarithm is limited. Okay. In which case, log base b of x, my x has to be greater than 0. Think about this. Think about what this graph looks like. If I just have a generic logarithm, I've got that vertical asymptote, and my graph looks like this. So my domain has to be greater than 0. Okay? So super important to remember that we have to check our answers on these logarithmic equations. All right. Let's see this in action. Okay, we want to solve log base 4 of x equals 2. Now, if we look at this equation, it has a single logarithm on the left and we have a constant on the right. We are going to simply rewrite this as an exponential function playing that circle game. We are going to get that 4 squared equals x. What's 4 squared? 16. I get that 16 equals x. Let's check it. The way that I am checking it is I am plugging that 16 back into my argument. So if I plug 16 in for x, is 16 greater than 0? Yes, it is. Okay, let's explore that a little bit in more depth so you don't try to generalize that too much. Okay, my argument has to be greater than 0. In this case, my argument is x, so x has to be greater than 0, and we just found out that x was 16. Is 16 greater than 0? Yes, it is. Cha-ching! All right, let's try another one. This time I have log base 2 of x equals -3. We have a logarithm on the left, a constant term on the right. We are playing the circle game. We get 2 to the -3 equals x. What's 2 to the -3? Remember that negative exponent's going to use the reciprocal. 2 cubed would be 8, but now I need the reciprocal of that, so it's going to be 1/8 equals x. All right, let's check it. My argument has to be greater than 0. Now remember, when I say that word argument, we're not fighting. We're looking at what I'm taking the logarithm of. In this case, it's that x. So my argument has to be greater than 0, which means my x is greater than 0. Is 1/8 greater than 0? It is. We are good to go here. All right. Now we have log base 5 of 8 minus 7x equals 3. We are still in the setup in which we're going to play the circle game to turn it into an exponential function. Notice though this time my argument is this entire 8 minus 7x. Okay, so as I play this circle game, I'm going to have 5 cubed equals 8 minus 7x. 5 cubed is 125 equals 8 minus 7x. And now let's solve this equation. We're going to subtract 8 from both sides. We get 117 equals negative 7x. We divide both sides by negative 7. And we get that negative 117 over 7 equals x. Let's check it. Remember that my argument, which is what I've got highlighted in yellow, has to be greater than 0. So 8 minus 7x has to be greater than 0. I just found that x was negative 117 over 7. 8 minus 7 times negative 117 over 7. We have to figure out if that's greater than 0 or not. To be honest, I don't really care what it is. I just care whether or not it's greater than 0. Okay? So think this one through. I have a negative times a negative, which is going to make this a positive. So right away now, I know that I have 8 plus some number. Is that going to be greater than 0? Yeah, it is. Okay. We also could cross reduce these 7s pretty easy and do 8 plus 117. That is definitely greater than 0. So 8 plus 117 would give me 125, and that is definitely greater than 0. So notice that I got out a negative answer, but once I plug it back into that argument, it does end up, the argument ends up being greater than 0, so we're good to go on that one too. All right, moving right along. We now have log base 2 of x minus log base 2 of 6 equals negative 1. This right now is not really in either of the forms that we discussed, but we can make it in the form we need. If I check out this left-hand side of my equation, I have 2 logarithms of the same base being subtracted. How can I squish them down into one logarithm? I'm going to divide the arguments. So this is going to be log base 2 of x over 6 equals negative 1. Now I have that single logarithm equaling a constant, and I can play the circle game. We get 2 to the negative 1 equals x over 6. Remember, 2 to the negative 1 just means I'm going to use that reciprocal. 2 to the first would be 2, but the reciprocal is going to give me a 1/2 equals x over 6. Trying to get that x by itself, it's connected to my 6 by division. So I'm going to use some multiplication here. Half of 6 is going to give me that 3 equals x. Now, when I did 1/2 times 6 in my mind, I just thought, what's half of 6? That's 3. We also could have done some cross reduction back here. 2 goes into 6 3 times. We also could multiply straight across the numerator and the denominator. Get 6 over 2, which would then reduce to 3. So you got some options there of how you can think about that. But either way, we should get 3 as a solution. Let's check it. Now, I have 2 arguments that I have to check here. Okay? I have x and I have 6. We don't really have to check the 6 though, because there's no variable in it. Okay? So, when I check this, I need to make sure that my argument's greater than 0. So that means I need x to be greater than 0, and 3 is greater than 0. So we are golden here. All right, similar setup here. We've got some bigger arguments to deal with here though, but we're going to combine those left-hand argument or logarithms. We have log base 4 of x minus 3 plus log base 4 of x plus 3 equals 2. My logarithms on the left-hand side have the same base, and they're being added, so I can squish them down into 1 using multiplication. So I'm going to have log base 4 of x minus 3 times x plus 3 equals 2. Now, I use some brackets there just to kind of differentiate that layer between parentheses and then a bracket. You could use another set of larger parentheses there too, same thing. We've got a single logarithm equals a constant. Here we come, circle game. 4 squared equals x minus 3 times x plus 3. Okay, now 4 squared is 16. Let's go ahead and FOIL out or simplify that x minus 3 times x plus 3. We're going to find that when I do my first, outer, inner, and last, my outer and my inner cancel. Remember, this is a factorization, a difference of squares. So I'm going to get an x squared minus 9. Okay, I have a degree 2, a quadratic equation. Okay, we've got several different approaches of how we could solve this at this point. We could get everything equal to 0 and try to factor it. We could try using the quadratic formula. But in my opinion on this one, the easiest thing to do is going to be to use the square root property. The reason that's true is because notice I have x squared, and then the other pieces are just numbers. There's no x. So if I add 9 to both sides here, I'm going to get 25 equals x squared. Now, in order for me to undo that square, I'm going to use a square root. Remember, when I use my square root, what do I have to include? That's right, plus or minus. So I get plus or minus the square root of 25 equals x. Square root of 25 is 5, so I get plus or minus 5 equals x. Now, just like before, if we're writing this by hand, I'm perfectly happy for you to write plus or minus. Our homework platform is not going to let us do that, though. We're going to have to write a positive 5, comma, negative 5. We get 2 solutions here. We have to check both of them. Okay, let's check 5 first. And then let's check negative 5. Remember that when I plug this into my argument, and I have 2 arguments I have to look at here, they have to be greater than 0. Okay, so if I plug 5 minus 3 and see if it's greater than 0. That's going to work out. 2 is greater than 0. Cha-ching! Now I have to plug it into my other argument. 5 plus 3, is that greater than 0? Yes, definitely. 8 is greater than 0. Cha-ching! Got to check negative 5. Negative 5 minus 3, is that greater than 0? No way, Jose. Because my negative 5 didn't work in my first argument, I actually don't even have to check it in my second argument. We could, just for good measure, if we were to do that, here, let's say negative 8 is greater than 0. No. Okay. If we were to plug it into my second argument, I would have negative 5 plus 3. That still is not greater than 0. Okay. So we are going to find that negative 5 does not work as a solution. That means the only answer that I'm going to use as a final solution here is going to be that x equals 5. Okay. So super important that we're checking our answers here on these logarithmic equations, because sometimes when you plug them back in, they're not going to work. All right, let's check out the ln of x minus the ln of x minus 4 equals the ln of 3. Now, notice that all of these are natural logs, so that's working in my favor. But it would be really nice if I had a single logarithm on the left and a single logarithm on the right. I can make that happen. Over there on the left-hand side of the equation, I have 2 natural logs that are being subtracted. So I can squish them down into 1 using division of their argument. So this would be the ln of x over x minus 4 equals the natural log of 3. Because I have a natural log on the left and a natural log on the right, I can go ahead and set their arguments equal to each other. So I'm going to have x over x minus 4 equals 3. Now, we've got some options here how we could solve this. We could multiply both sides by x minus 4 to get rid of that denominator. We also could think of this 3 as 3 over 1, and then we could cross multiply. So we'd have 3 times x minus 4 equals x. Either way, we're going to come up with the same equation in the next line. Let's distribute that 3. We get 3x minus 12 equals x. All right, I want to get that x by itself, and I want to move that 12 over to the other side. Be very careful here, because when I subtract x initially, this is going to give me a 2x minus 12 equals 0. And now I'm going to add that 12 to the right, and I'm going to get 2x equals 12. All right, divide by 2, and I get that x equals 6. Let's check it. Remember, I have 3 arguments here. I'm not going to worry about the 3 because there's no variable in there. But I do need to worry about the x and the x minus 4, so I've got to check this in 2 places. Okay? X is greater than 0. 6 is greater than 0. Cha-ching! X minus 4 greater than 0. Is 6 minus 4 greater than 0? Yes. 2 is greater than 0. Cha-ching! So, x equals 6 is in the clear as a final solution there. All right, we've got one last problem to work through. This is log base 3 of x plus log base 3 of x plus 1 equals log base 3 of 2 plus log base 3 of x plus 3. This one looks long, but I promise you it's not so bad. All of these are log base 3. On the left-hand side, I have 2 logarithms being added. I can combine them into a single one by multiplying their arguments. Exact same thing on the right-hand side. 2 logarithms of the same base being added, I can squish them down into one with their arguments being multiplied. So that's our first step right there. We are going to have log base 3 of x times x plus 1 equals log base 3 of 2 times x plus 3. All right, if you're comfortable with it, some of you may have already gone ahead and done that distribution at the same time, but we're going to get log base 3 of x squared plus x equals log base 3 of 2x plus 6. Now, these logarithms are the same base. We have a single log base 3 on the left and a single log base 3 on the right. What can we do with our arguments? You got it. We need to set those arguments equal to each other. So we get x squared plus x equals 2x plus 6. This is degree 2. So I've got some options. I might want to make it equal 0 and try to factor it. I could try using that quadratic formula. We could graph it. We can complete the square. You guys know that list. We've seen it before. In this case, I'm going to get this all over the left-hand side, and I'm going to make it equal to 0. And I'm going to try to factor it and see what works. All right. So if I start moving things over the left-hand side, I'm going to get x squared minus x equals 6. Let's subtract that 6. I'm going to get x squared minus x minus 6 equals 0. This one looks like one that's going to work out in our favor here. Remember that trinomial is going to break down into my two empty sets of parentheses. If I look at that first term, x squared, let's break it down into x and x. And now I'm checking out that last term, which is minus 6. What would multiply to negative 6, but when I add them together, I check that outer and that inner, would add to negative 1. Remember, there's like an invisible negative 1 here. Yeah, I need x minus 3 and I need x plus 2. All right, I set each set of parentheses equal to 0 now. I have x minus 3 equals 0, x plus 2 equals 0. I get 3, and I get negative 2. Let's check them. I have to check all of these arguments. Only one I'm off the hook for is that log base 3 of 2 because it does not have a variable in it. Okay, so let's check these separately. We're going to check our 3, and we're going to check our negative 2. All right, if I check 3, first one up is x is greater than 0, so 3 is greater than 0. It works. X plus 1 greater than 0. That's 3 plus 1 greater than 0. Yep, 4 is greater than 0. We're in business there. And then we got to check x plus 3 is greater than 0. 3 plus 3 greater than 0. Yes, 6 is greater than 0. So x equals 3 is going to be a confirmed answer once we check it. Let's check negative 2. X greater than 0. Is negative 2 greater than 0? No. As soon as I find that it does not work, I do not need to check the rest. I can if I want for good measure, but as soon as you find one that doesn't work, it does not work. If I were to plug in negative 2 to the other pieces, I am going to find that one of the arguments works, one of them doesn't. But again, as soon as one argument does not work, that entire answer is out the window. So x equals negative 2 is not going to be a solution here, only x equals 3. Super important to check those answers.